We're going to discuss ways of calculating the magnetic field in a very long solenoid. First, we'll use a simple application of Ampere's law, which you'll have seen several times before, and then we'll build up the magnetic field by considering each turn in a solenoid as a magnetic dipole. So just to remind you that a solenoid is a tightly wound coil of wire which we will say has n turns in total. It has length L. That doesn't look quite right. Let's put it. No, that's an N, not an L. It has a length L, and it carries a current I. And of course, if you just think back to some of your elementary electromagnetism, you'll remember that you find that the magnetic field is B is mu naught I n over L in the z direction, and we assume that this is oriented along the z-axis. That's the field inside the solenoid, and it's assuming that it's a very long solenoid and you're a long way from the ends. So let's just think, first of all, let's remind ourselves about Ampere's law and think about why we get that result. So if we consider Ampere's law, the first thing we have to do is to think about the field, because what we're going to want to do is we're going to start with the simple idea of curl B is mu naught J. We're going to, of course, translate that into an integral form, which is going to be the closed loop integral of B dot dl is equal to mu naught times the current I. Though, of course, actually, we're going to have to think rather carefully about what we mean by I, and notice that this I here is not the same as this I here. This is the current I flowing through the surface. So let's put a little subscript on it, S, just to make that one clear. We haven't yet defined the surface or the loop. So we're going to assume that we've got a coil like this, and that's along the z-axis. So when we draw that in cross-section, we'll have the wires here. And what we're going to want to do is to do an Amperian surface. Actually, let's just do the surface in a different colour. Let's do that in green. We have an Amperian loop with a surface drawn like that. So that's the surface C. Sorry, the loop C. The surface of S, of course, just cuts through that loop. Okay, so what can we say about the field? Well, the field must be along Z, simply from symmetry arguments. If you have an infinite solenoid, and you have it in a circular shape, in a cylindrical shape, then you have rotational symmetry about the z-axis, you have translational symmetry along the z-axis, and therefore the only direction the field can be is along the z-axis. So that's the first thing that we've managed to establish. The second thing is that we can argue with complete certainty that B will tend to 0 as we go very far away. So far from the solenoid, and let's just define that. Remember, we're working with cylindrical polars, so what we're going to have here is that we're going to have an R, capital R, a phi and a Z, and so in this case here, where we're saying B goes to 0 far from the solenoid, that means as R tends to infinity. Now, if we now think just briefly about an Amperian loop outside the solenoid, we can put that essentially anywhere and we won't be cutting any current. Therefore, we can say that B must be equal on both sides of the loop. Outside the solenoid, if it goes to 0 as we go to infinity, then we can deduce that B must equal naught at all points outside an infinite solenoid. And if you think about the shape of a magnetic dipole's fields, and then just stretch it so that you get the traditional fields of a bar magnet, then what you'll find, let me just sketch that down here. So here's a little bar magnet with a north and a south, which of course a solenoid is effectively equivalent to. What you find is that you have field lines that loop around like this. And okay, so that's not, oh dear, delete deleted rather more than I wanted to there. So what we find is that the field lines look like this. Now, obviously the field there is not 0 outside, but as the length of the bar magnet, L, gets larger, you'll find that the field lines become more dilute in the radial direction. And therefore, as we take the length to infinity, we end up with 0 field outside. That's just a little digression. So I'll put that into square brackets. Okay, so we now have the fact that B is 0 outside. We could, if we wanted to, label this, this loop with a set of letters A, B, C, oh dear me, that's awkward, A, B, C and D. And actually, let's just change those. Let's get rid of those so we can keep the name for our loop as C. So this loop is going to be C, and I will say that the points are 1, 2, 3 and 4. As we go around the loop, we can say that we will get contributions to the integral from the line 1 to 2 and from the line 3 to 4. The lines 2 to 3 and 1 to 4 will give us nothing because they will be perpendicular to the fields. We've just argued actually that 3 to 4 will go to 0, so the only contribution that is left is from the line 1 to 2, and therefore we can say that B inside the solenoid multiplied by the length of that loop, L, must equal the total current which is passing through the surface. So there's the mu naught, of course, there. Now the total current passing through the surface is n over L, so that's the number of turns divided by the length, so that's turns per unit length, multiplied by the length, multiplied by the current per turn. And from there we can see that B is equal to mu naught Ni over L in the Z direction. You'll have seen that before. I just wanted to go over the details to make sure that the key ideas were clear. Let's now turn to a solution using the vector potential of a dipole. We're going to work in cylindrical polar coordinates simply because that's easier for the symmetry of the solenoid. We're going to use the vector potential of a dipole, and then we're going to sum over contributions. Now, we found in other places that we can write the vector potential of a dipole in the following way: mu naught I a squared over 4, and then we have an r over r squared plus a squared plus z squared to the 3 over 2. A is the radius of the dipole. And what we want to do now is we're going to say that we're going to be near the axis of the solenoid. That simplifies things, and that's really where we're interested in the field. So what we're going to say is that R is very much less than A. That's the condition that puts us near the axis. And in that case, we can write our vector potential as mu naught I a squared over 4. We retain the r on the top, the key point is on the bottom. We end up with just an a squared plus z squared to the 3 halves. You need to keep that in mind. Now, if we use the standard formula for curl in cylindrical polar coordinates, we find that B, which is equal to curl A, has 2 components which are non-zero. So we have the radial component, and remember this is the cylindrical radial, which is mu naught I a squared over 4, and we get a 3, let me make my 3 just a little bit clearer, 3z r over a squared plus z squared to the 5 over 2, and B in the z direction is mu naught I a squared over 4, and then you have a 2 over a squared plus z squared to the 3 halves. That's just due to the current ring. If we look at that, what we can see is that if we are near the axis, i.e. r is small, then BR is going to be quite small generally, certainly when r is equal to 0. So on the axis we'll be entirely axial, and we're going to explore what happens as we integrate over the entire solenoid to see how that behaves. So to do that, we're going to integrate over the solenoid, over the length. We want to, oopsie, that's not quite right, over the length. Let me just fill that gap in there. We're going to replace, excuse me, Z with Z1 minus Z2. So Z1 is going to be the observation point, and Z2 is going to be the source point, the current point, source of the current. And so what we would say then is that B at Z1 is equal to the integral from 0 to L n over L, that's then turns per unit length, multiplied by some small contribution dB, which we're going to take from those formulae up there, as a function of Z1 minus Z2. And then there's going to be a dz2 integrating over it. So, if we're on the axis, where r is equal to 0, then BR is equal to 0. That just comes from the formula there. Capital R is 0, then BR must equal 0. If we're at the centre, and we'll see this in a minute, so at the centre what we mean is where Z is equal to L over 2. That's going to be Z1, so we're level with the centre. Then again, BR must equal 0. You can see that because the integral for BR is odd, and therefore the integral of an odd integral between even limits is always 0. And we don't expect it to remain axial near the ends, but we can't use these formulae near the ends, or we certainly can't use them near the ends far away from the axis. So let's just look at how we would evaluate the total field. Let's start with BR at Z1. That's mu naught IA squared multiplied by n over 4L. We have the integral from 0 to L of 3 Z1 minus Z2 divided by A squared plus Z2 squared, sorry, Z1 squared minus Z2 squared. No, that should be Z1 minus Z2 with a squared outside. This is getting a little bit cramped. Let me rewrite that. So we get Z1 minus Z2 all squared, and then that's to the 5 over 2 dz2. That's a simple integral. You end up with a mu naught IA squared Rn over 4L, and then you have a minus 1 over A squared plus Z2 squared to the 3 halves, and I've also just shifted the origin to L over 2, so L over 2 plus delta, and you have minus L over 2 plus delta. So I'm assuming that Z1 is L over 2 minus delta. So we're just away from the centre of the solenoid. And under those circumstances, you can see that BR will essentially tend to 0. So the field is axial. And that's true for a finite but long solenoid, as well as the infinite solenoid, which we deduced using Ampere's law. You can deduce the value of this axial field Bz at Z1 by integrating in the usual way mu naught IA squared n over 4L integral from 0 to L of 2, divided by A squared plus Z1 minus Z2 squared to the 3 over 2 dz2, and we make a substitution here. We substitute Z1 minus Z2 is equal to A tan theta. And when we do that, then we find that Bz at Z1 is mu naught I a squared n over 4L integral between theta 1 and theta 2, which you can define fairly easily, 2 over a squared cos theta d theta, which is easily evaluated to mu naught I n over 2L into sine theta between theta 1 and theta 2, and as theta 1 goes to minus infinity and theta 2 goes to infinity, which is another way of saying that L goes to infinity, this becomes mu naught I n over L. That's easy to show. So, what have we seen? We've seen that we can start with a fairly simple argument using Ampere's law, that's up here, and using Ampere's law we can deduce the field outside an infinite solenoid. We've then done things rather more carefully. We've started with the vector potential for a dipole, keeping it in cylindrical polar coordinates. We've derived the B field, the magnetic field, using the curl. We've then integrated over the length, adding up all of those different contributions. We've looked at some simple evaluations of the integrals and the symmetries, and we've come to the same conclusion, which is reassuring but not surprising. So that finishes what we've been talking about in terms of the solenoid. It's just important to note that the solenoid can also be shown to be effectively a mapping onto a bar magnet where the current is no longer the current due to an external field, an external current, but is a magnetization current.